Hello, welcome to this section 2.2 lecture video. So last time we started talking about the idea of average rate of change, which is something we're going to use in more detail and kind of build out throughout this chapter as we head towards the idea of the derivative, which is what chapter 3 is about. So one of the concepts we discussed as we were talking about this was when we were talking about the tangent lines is we talked about the idea of a limiting factor. Basically, what happened is we let the 2 points get really, really close together. The distance between the 2 points go to 0. Well, what we're going to talk about in this section is start to formalize this idea of finding limits and what a limiting factor actually is. So at this point, you can go ahead and open up your note sheets to section 2.2. Noted these note sheets can be found either in Blackboard or on my math lab, not necessarily in both, but in one of those two places. So you can follow along with these. So suppose that f of x is defined on an open interval c, open interval about c, except possibly it's c itself. If f of x is arbitrarily close to the number L, as close to L as we like, for all x sufficiently close to c, other than c itself, then we say that L approaches the limit L as x approaches c, and write the limit as x approaches c of f of x equals L. Okay, so that's the idea. So one of the things we can talk about here is this idea of limiting value. So if I wanted to, for example, figure out the limit of this expression here, so I want to define the limit as x approaches 1 of x squared minus 1 over x minus 1. So that's what we're going to try and figure out, is fill in that blank. Well, the first problem is I can't find f of 1, right? Because what happens if we try to find f of 1? We get 0 over 0. Well, that is undefined. Okay, so we can't just plug in the value. But what we can do is we can try to see, well, what happens as we get close to 1? So like, for example, if I graph this, so I'm using the Class Calc app, which you can download from the internet, and I have a link for this in the Blackboard course. So if we put in this graph, so I go to the graph and I type in x squared minus 1 over x minus 1. Sorry, minus 1. Okay, so what we should notice here is even though we know that we can't plug in the value 1 into this function, we can, and in fact, if you notice as I try to graph this, it's not giving me any y values. We can tell that as we get close to 1 here, we're getting, and it won't actually let me get 1 itself. As we're getting close to 1 here, we could tell that there is some value that the graph approaches, right? Okay, so let's go ahead and look at that by creating a table of values for this. So like, for example, if I plug in different values for x, they get closer and closer to 1. What happens? Okay, so we could try some values. So let's just pick some values bigger than it. So if I plug in 2, that would be 4 minus 1 is 3. 3 divided by 1, so that would be 3. Okay, and then we could try 1.5, and then we could try 1.1, and then we could try 1.01. So let's just plug those in using our calculator. So let's go to the graphing calculator, and we can plug in those different values. So for the first one, we get 1.5 squared minus 1 over 1.5 minus 1. So that's 2.5. And then if I double click on what I just typed in, I can get it to just pop down here again. So I can just change this to 1.1. Whoops, sorry. Let's edit that. So 1.1, so that's 2.1. And then if we do the same thing again, and I just add in zeros here, I get 2.01. Okay, so 2.5, 2.1, 2.01. And so what you should notice is as we get as we're getting closer and closer to 1, as x gets closer and closer to 1, what are the f of x getting closer and closer to? And if you needed one more value, you could add one more value. Okay, so 1.001. So we could do the same thing, just show how much it's getting closer. And if we do that, we get 2.001. Okay, so you can see that as we get closer and closer, we're getting closer and closer to 2. And so that would be the limit of this function. So that's the idea of what we're looking for. So is there a value that the function approaches as you allow the x value to approach some number? And there are two basic functions that have useful limits for us that we're going to use as we move forward here. So the first one is called the identity function. And so the idea here is that f of x equals x, so no matter what number you plug in for x, you get x out. And then the other one is the constant function. And so the idea for both of these is that the limit as x approaches c of x, well, if x is getting close to c, then what's x getting close to? Well, it's getting close to c, right? So that limit would be c. So the identity function, its limit is simply whatever number you're approaching. And then the constant function, the limit as x approaches c of k. Well, if k is a constant number like 2, then no matter what x is, k is always going to be 2. So the limit of that function will always just be whatever k is. Okay, so the limit of x is simply whatever value you're approaching, and the limit of a constant k is just that constant k. Now, here are some examples of what could happen where we might not actually get a limit. So if you look at these, the first one has a little step to it. So as x approaches 0, what happens on the left-hand side, we're getting close to 1, but down here on the right-hand side, we're getting close to 0. So is there a number that both sides of the function approach? And the answer to that is no. Okay, so that's why it doesn't have a limit. So if the graph approaches two different points, as you get close to that x value, that gives you not a limit. Another example is when we're dealing with infinities. So as we get close to 0 in this second one, this graph goes to positive infinity, and this graph goes to negative infinity. So it diverges in two different directions, so that means that wouldn't have a limit, right? It doesn't approach one single point. And then another idea is something that oscillates too much, and that's what's happening in this last one. So notice this graph bounces back and forth between 0 and -1, so as we get closer and closer to 0 on the right-hand side, we're approaching all the values between 0 and -1. So there isn't one value that we're approaching. So let's look at an example of that. So here are some true or false statements. So the question is, just to answer these is either true or false. So the first question says, the limit as x approaches 0 of f of x. So if this is my function f of x, as we get closer to 0, from both sides, what number are we approaching? And the answer is 0, right? This graph gets closer and closer to 0 as we get. So that's true. There is a limit because it approaches the same number from both sides. And then what is that limit? That's what these next two are about. So what number does the graph approach as we get closer and closer to 0? Well, the answer to that is 0. So this one would be true, and this one would be false. And similarly, if I jump down here a little bit, we can talk about these f of 0 ones. So is f of 0 0? Well, if you look at the graph, that's an open circle. So at f of 0, we actually get the value 1. So this first one is false, and the second one is true. So f of 0 is not 0, it's 1. So the limit is different than the actual function value, which is perfectly okay. Okay, so go ahead and pause the video at this point and try these other problems. See if you can figure those out. Okay, so now that you've had a chance to try them and you've started the video back up, let's go through them together. So now we're talking about this point over here. Okay, we're talking about over here. We're looking at right here. What happens as we get close to 1? So is the limit as f of x equals 1? Well, as we get close to 1 on the right side, it sure looks like we don't approach 1, right? We actually approach 0. And on the left side, we approach negative 1. So this limit is definitely false because on neither side, it approaches 1. But this second one is also false because it doesn't approach 0 from both directions. From the left, it approaches negative 1. On the right, it approaches 0. So that's false. So I'm going to skip this next one for a second. I'm going to go to the limit of x of 1 does not exist. And the answer to that is true. There is not a limit at 1 because the graph approaches 2 separate points. So that allows us, and then I'll go ahead and do these last 2 and then come back to the one I skipped. So then f of 1 is 0 or f of 1 is negative 1. Well, f of 1 is in fact 0, so this one is true and this one is false, right? Because when we're talking about is, I'm looking for where is the filled in circle. And then the last question says the limit as x approaches c of f of x exists at every point in point C in negative 1 to 1. So what that's asking is, if I look at this part of the graph, negative 1 to 1, does the limit exist at every point? In other words, for every point on the graph, do I approach some value from both directions? The answer to that would be true, right? Because every point in this has a limit. Now, could I say that there is a limit for every point of this entire graph? The answer would be no, because at 1, we run into a problem. Okay, so if I were to ask the same question, except say the limit as x approaches c of f of x exists at every point C in negative 1, 2, the answer to that would be false. Because there is the limit as x approaches 1 of f of x does not exist because it jumps. Okay, so this is really what we're looking out for, is are there jumps in the graph? Anywhere there's a jump, not just skipping over a single value but leaping like this, you're going to not have a limit. So now let's talk about, well, how do we find these limits? Is there an algebraic approach to finding limits? And there is. So there are 2 limits. We already know what they are. The limit of the variable x and the limit of the constant k. So what we'd like to be able to do is we'd like to break down any limit expression we see into expressions that we know the limits of using this idea. And that's where these limit rules come in. So if my limits are defined as L and M, then the limit as x approaches c of f of x plus g of x is simply L plus M. In other words, it's the limit as x approaches c of f of x plus the limit as x approaches c of g of x. So we can break an addition up inside a limit into 2 separate limits. So the goal is to end up with a bunch of less complicated expressions inside of limits. So take a complicated expression inside a single limit and end up with a bunch of limits that have easy to find the limit of expressions in them. The difference rule works the same way. If the limit as x approaches c of f of x minus g of x, that's just going to be L minus M. If we have a constant times a function, such as the limit of x approaches c of k times f of x, then that's just going to be k times L. K times whatever the limit of f of x is. The product rule says that the limit of the product of 2 functions is just the product of their 2 limits. The quotient rule works the same way. It's just L divided by M. And there's one thing here is g of x cannot equal 0. Okay? Or I shouldn't say g of x can't equal 0. The limit can't equal 0. So M cannot equal 0. The power rule says the limit as x approaches c of f of x to the nth power is just L to the nth. And the root says the limit as x approaches c of the nth root of f of x simply equals the nth root of L. Okay. So these are all rules we can use to break up complicated expressions into simpler limits. So for example, if I take this first one here, I could break these up step by step or do it all at once, but let's go and do the first one step by step. So what I want to do is I want to make this into a more simpler limit. Well, I know I have the root rule, so that says that the limit of a square root would be the square root of the limit. Okay, and then I know I have the difference rule, so that says the limit of a difference is the difference of the limits. So this would be the square root of the limit as z approaches 4 of z squared minus the limit as z approaches 4 of 10. And then I know that I have the power rule, so the limit of z to the z approaches 4 of z squared minus the limit as z approaches 4 of 10. Okay? And now I have two basic limits that I know how to find using the rules we said before. We know the limit as z approaches 4 of z is just 4, right? The limit of a variable is just whatever the variable is approaching. And I know the limit of a constant is just that constant, no matter what value it's approaching. Okay? So we can plug those in, and what we get for our limit is going to be the square root of 4 squared minus 10, which in this case is 16 minus 10, which is the square root of 6. And so there's our limit. Okay, so that's fairly straightforward, and most of these will be like that. Now, the second one here runs into a problem that we're going to need to address, which is, if we look at the second one here, notice that if I tried to just break this all down using limits, so I'm just going to write this out, but then I'm going to erase it. If I broke this down doing limits, I can break up a root, I can break out a difference, a sum, a product. This would be the square root of 5 times the limit as h approaches 0 of plus the limit as h of h, sorry, I forgot an h in there. The limit as h approaches 0 of 4 minus the limit as h approaches 0 of 2 over the limit as h approaches 0 of h. Now we can substitute in, and this is the square root of 5 times 0 plus 4 minus 2 over 0. And that's where the problem comes in. Because notice I'm dividing by 0, which is undefined. And this is one of the things we pointed out on the last page. The limit of the denominator with the quotient rule cannot be 0, which is the problem here. So before we take this limit, what we want to do is we need to rewrite this expression in a way that we won't run into that problem. And we can use one of the things we talked about in the last section, which is multiplying by the conjugate. So go ahead and multiply by the square root of 5h plus 4 plus 2 over the square root of 5h plus 4 plus 2. And this will be a pretty common general way to deal with things with radicals like this and division. Okay, so we multiply that out, and so that's the limit as h approaches 0 of multiply this out. Remember, the middle two terms are going to go cancel each other. But I've got the square root of 5h plus 4 times the square root of 5h plus 4, so that's 5h plus 4. And then I'm going to have a negative 2 square root and a positive 2 square root, so those will cancel. And then negative 2 times positive 2 is negative 4 over h times the square root of 5h plus 4 plus 2. And so now we can start doing some simplification. So this is the limit as h approaches 0 of 5h, because the 4 and negative 4 cancel, over h times the square root of 5h plus 4 plus 2. And now I can cancel the h's. So this is the limit as h approaches 0 of 5 over the square root of 5h plus 4 plus 2. And now if I plug in 0 to the denominator, I'm not going to get 0, so I'll be okay. So we can come up over here, and I can rewrite this limit using the rules. Now, I'm not going to go step by step like I did in the previous one. I'm just going to go ahead and write this out. So I can use the quotient rule to break it into 2 pieces. I can use the sum rule to break the bottom into 2 pieces, and then I can deal with the inside the radical. So this would be the limit as h approaches 0 of 5 over the square root. I made that way too big. The square root of 5 times the limit as h approaches 0 of h plus the limit as h approaches 0 of 4 plus the limit as h approaches 0 of 2. And now I wrote out this step, but once you get used to this, you'll notice that really all you're doing is plugging in the 0 in for the variable. All right, because the limits that are constant are going to stay the same, and the limits that have the variable are just going to get whatever the h is approaching plugged into it. So in this case, that's 5 over the square root of 5 times 0 plus 4 plus 2. So that's 5 over the square root of 4 plus 2, which is 5 over 2 plus 2, which is 5/4. Okay, and so that's what we're really looking for here, is this idea that we can really just, for the most part, these limit rules just allow us to plug in the value into the function. But let's go and practice that a little bit more. So I want you to pause the video at this point, see if you can rewrite these limits for the last 2 using this idea of the limit rules. You can go step by step or just write it all out, but I want you to write out the limit in a more expanded form that we can take the limit of and then find the limit. So go and pause the video and try that. And when you're ready, hit play and we'll talk about these. Okay, so now that you've gotten a chance to try these, let's go through them together. So this one, I can use the sum and different rules to break this up into 4 limits. And then I can use the constant multiple rules and the power rules to get these first 3 terms down to the limit of x. And the last one will be the limit of 8. So this will be the limit as x approaches -2 of x cubed minus 2 times the limit as x approaches -2 of x squared plus 4 times the limit as x approaches -2 of x plus the limit as x approaches -2 of 8. Okay, and the 4 limits we have left are all limits we know how to do, right? The limit as x approaches -2 of x is just -2. And the limit as x approaches -2 of a constant is just a constant, so in this case 8. And then we can simplify. So -2 cubed is -8. -2 times -2 squared is -8. 4 times -2 is -8. Plus 8, and so we get -16. Okay, so that's the idea. So same idea would work for the last one, right? So this would be the limit as x approaches 2/3 of 8 minus 3 times the limit as x approaches 2/3 of s. Oh, except there's a typo here. One of these needs to be, we need to be using the same variable. So I'm just going to use x for all of them. Of x times 2 times the limit as x approaches 2/3 of x minus the limit as x approaches 2/3 of 1. Okay, and then those are all limits we know, right? The limit as x approaches 2/3 of 8 is 8. The limit as x approaches 2/3 of x is 2/3. The limit as x approaches 2/3 of x is 2/3. And the limit as x approaches 2/3 of 1 is 1. So this would be 8 minus 2 times 4/3 minus 1. So that's 6 times 1/3. And so that is 2. Okay, so that's the idea. So for the most part, when you deal with limits, all you're really going to need to do is plug in the value of c into the expression, and that will tell you the limit. It's good to know how to use the rules, but the upshot of using the rules is the idea that you can most of the time just plug the value in. When you run into trouble is like in the second one here, when the denominator would be 0 if you just plug the value in. So other types of functions where we're going to need to do some work are rational functions. Okay, so we're going to practice with this idea some more. So remember, what you want to be careful of is if you were to plug plug the value in, would it make the function 0? So like for this first one, you could just go ahead and check. Is what happens if I just plug the value in? So in this one, it would be negative 1 squared plus 3 times negative 1 plus 2 over negative 1 squared minus negative 1 minus 2. So this would be 1 minus 3 plus 2 over 1 plus 1 minus 2. So that's 0 over 0. Okay, and so that's not going to work because that's undefined. So we need to figure out, is there a way to simplify this or write this another way before we tell the limit? Most of the time when you have a polynomial divided by a polynomial, what that's going to entail is factoring. Okay, so we have to go back to our college algebra days and factor a little. So to factor this first one, we simply can use the simplified AC method, which just means find two numbers that multiply together to get 2 and add to get 3. So in this case, two numbers that multiply to get 2 and add to get 3 are 2 and 1. So this would be t plus 1 times t plus 2. And we can use the same idea on the bottom. So two numbers that multiply to get negative 2 and add to get negative 1 are t plus 1, are positive 1 and negative 2. So it would look like that. And now we can simplify, right? Because t plus 1 and t plus 1 cancel. So this is the limit as t approaches negative 1 of t plus 2 over t minus 2. So that would be negative 1 plus 2 over negative 1 minus 2. So that would be 1 over negative 3, which is negative 1/3. Okay, so that's the idea. So when you're dealing with these rational functions, most likely what you're going to need to do is factor. So let's try another one together. So here, same problem would happen, right? If I plug 2 into the bottom, 2 to the 4th is 16. 16 minus 16 is 0, so that's a problem. So I want to factor. So we can do the limit as v approaches 2. To factor the top, we have to use the difference of cubes rule, which you can look up online or in chapter 1 of this book. So the difference of cube rule says that we take whatever's being cubed and minus the whatever's being cubed. These are both perfect cubes. So that would factor as v minus 2 times v squared plus 2v plus 4 over, and we can factor the bottom using the difference of squares. So that factors as v squared minus 4 times v squared plus 4. And then we can actually factor the bottom again. So this would be the limit as v approaches 2 of v minus 2 times v squared plus 2v plus 4 over, using the difference of squares on the first part again. So v minus 2 times v plus 2 times v squared plus 4. And so now we can cancel out a v minus 2 and plug in 2 into this function. Okay, so this would be 2 squared plus 2 times 2 plus 4 over 2 plus 2 times 2 squared plus 4. So that's 4 plus 4 plus 4 over 4 times 8. So this is 12 over 32, which is 3, 6, 1. No, sorry, that can't be right. 3/8. Okay, and then the last one here is another example where we're dealing with a square root inside of a radical. Almost always that's going to mean you're going to need to multiply by the conjugate. So in this case, if I were to plug 2 in the bottom, it would be a negative 2 into the bottom. I'd get negative 2 squared is 4. 4 plus 5 is 9. The square root of 9 is 3. 3 minus 3 is 0. So that's a problem. So we can multiply by the conjugate. So that's the square root of x squared plus 5 minus 3. I mean plus 3, sorry, the conjugate. So I just need to change that middle sign. So this would be the limit as x approaches negative 2 of x plus 2 times the square root of x squared plus 5 minus 3 over x squared plus 5 minus 3. And then on the bottom, we can combine like terms. So this is the limit as x approaches negative 2 of x plus 2 times the square root of x squared plus 5 minus 3 over x squared plus 2. And now notice if I plug negative 2 into the function, it's not going to make the denominator 0. So we should be fine. So this will be negative 2 plus 2 times the square root of negative 2 squared plus 5 minus 3 over negative 2 squared plus 2. So that's 0 times 0 over 6, which is 0 over 6, which is just 0. Okay, so that's the idea. So go ahead, flip over to the next page, and try these ones that are similar to the ones on the previous page. Once you've tried those, you can unpause the video, and then we'll talk about them together. Okay, so now you've got a chance to try these. Let's go ahead and go through these together. So, step 1 for these first two is just factor, right? So this is the limit as x approaches negative 3. So we've got x plus 3 on top, and on the bottom, I need two numbers that multiply together to get 3 and add to get 4, and those are 1 and 3. So we can cancel those out. And so now this is the limit approaches negative 3 of 1 over x plus 1. Okay, and so now if I plug negative 3 in, we're going to be fine. So I can just plug that in. And so this is 1 over negative 3 plus 1, which is 1 over negative 2, which is negative 1/2. Okay. On the next one, what we want to do is we want to use the idea of factoring out a greatest common factor to start with. So this would be the limit as y approaches 0 of y squared times 5y plus 8 over y squared times 3y squared minus 16. And now the y squareds cancel. And now if I plug in 0 for y, we're okay, because we won't get 0 in the denominator anymore. Okay, so that would be 5 times 0 plus 8 over 3 times 0 squared minus 16. So that's 8 over negative 16, which is negative 1/2. Okay, and then in the last one, we're going to have to use the multiplying by the conjugate idea like we have in previous problems. So we're going to multiply by 2 plus the square root of x over 2 plus the square root of x. So that's going to be the limit as x approaches 4 of 4x minus x squared times 2 plus the square root of x over 4 minus x. And at the moment, we're still in trouble for this one because the denominator would still be 0 if I plug in 4. But if we factor on top, we can actually factor out an x, right? So that's x times 4 minus x times 2 plus the square root of x over 4 minus x, and now the 4 minus x is canceled. So this is the limit as x approaches 4 of x times 2 plus the square root of x. And now here we can finally just plug in 4. So this would be 4 times 2 plus the square root of 4, which is 4 times 4, which is 16. Okay, so that's the idea. Now, that's most of the ones you're going to run into, except for ones that involve trig functions. But the nice thing is all the rules still apply for trig functions, so these are really just going to work the exact same way as before, as long as you don't get something that's undefined. Okay, so for the first one, really all you have to do is plug in 0. So this is 0 squared minus 1 times 2 minus the cosine of 0. Okay, and so that's negative 1 times 2 minus the cosine of 0 is 1. So that's negative 1 times 1, which is negative 1. And so that's the idea. So these are going to work just like before. And in fact, in a lot of cases, you may be able to use or you can try and use a calculator if you want to, but they may not be that effective, especially because we are going to get fractions and radicals and irrational numbers for a lot of these answers. But the first one would have been fine. You could have just plugged that in your calculator with plugging in x equals 0. So, but same idea here, right? Secant squared of 0, right? If I want x to be 0. So that's the same thing as 7 plus 1 over cosine squared of 0. Well, and just like we saw in the previous problem, the cosine of 0 is 1, 1 squared is 1, so this is really just the square root of 8, which is 2 root 2, right? Because I can, 4 times 2 is 8, the square root of 4 is 2. So that's where we get the 2 times 2. Okay, and that's the idea. So why don't you try the other two real quick, and then pause the video, and then we'll go over them, and then we'll move on to the next thing. Okay, so this one, once again, just plug 0 into the function. The sine of 0 is 0. 0 squared is 0. Last one, just plug in 0 for tangent. Tangent of 0 is 0. So that's it. Okay. So, one of the things that we want to be able to do with this is what's called the derivative. And we're going to talk in detail about the derivative in Chapter 3. But what the derivative has to do with limits is it's actually going to be the limit of this function. So because of their connection with secant lines, tangent lines, and instantaneous rates, limits of the form, the limit is h approaches 0 of f of x plus h minus f of x over h are frequently done in calculus. And in fact, we did some of these in the last section, right? So we want to make sure we know how to do these. So that's what we're going to practice doing here. So if I want to find, if I want to evaluate this, all I do is plug in the information I'm given into this. So this would be the limit as h approaches 0 of the square root of 3 times x plus h plus 1, except I'm also going to plug in x, right? X is 0, so 0, 0 plus h plus 1, plus the square root of 3 times 0 plus 1, right? Because that's f of x over h. And then we're just going to simplify. So the limit, so this is exactly what we were doing at the end of the last section, but just more formalized now with this limit notation. So this would be the square root of 3h plus 1 plus the square root of 1, which is just 1, over h. And now I need to find that limit. As we've seen previously, anytime I'm doing a limit with a square root where h cannot be 0 right now, I want to multiply by the conjugate. So multiply by the square root of 3h plus 1 minus 1, or the square root of 3h plus 1 minus 1. Okay, so that's going to give me the limit as h approaches 0 of 3h plus 1 minus 1 over h times the square root of 3h plus 1 minus 1. Combine like terms on top and the 1's cancel. So this is the limit as h approaches 0 of 3h over h times the square root of 3h plus 1 minus 1. Now I can cancel the h's. So this is the limit as h approaches 0 of 3 over the square root of 3h plus 1 minus 1. And now I can just plug in 0 into the function. So this is 3 over the square root of 3 times 0 plus 1 minus 1. Uh-oh. Oh, whoops. Sorry. I did something wrong up here that's going to fix what was going to be a problem. These should be minuses, right? Because in the original function, it's a minus. So that should be minus. That should be minus. So these are pluses. And so that does not change the product here. That's still a minus 1. But on the bottom, this is going to be a plus 1, which is good. Okay, so this is 3 over the square root of 1 plus 1, which is 3 over 2. Okay, so that's the idea. So if you want to at this point, we did ones like these, similar to these in the last section. So you could go and pause the video and try these last two on your own. And then when you hit play, we'll go through them together. Okay, so let's go ahead and go through these. So this is the limit as h approaches 0. And we plug in x plus h first. So x plus h in this case is going to be negative 2 plus h squared minus, and then we do f of x. So f of x is going to be negative 2 squared over h. So that's the limit as h approaches 0 of 4 minus 4h plus h squared minus 4 over h. Combine like terms. So this is the limit as h approaches 0 of negative 4h plus h squared over h, which we can cancel out some h's now. So this is the limit as h approaches 0 of negative 4 plus h. Plug in 0, and you get the limit is negative 4. And then for the last one, this would be the limit as h approaches 0 of f of x plus h. So that's going to be 1 over negative 2 plus h, right? Because x is negative 2, minus 1 over f of x, so 1 over negative 2, all over h. So that'll be the limit as h approaches 0 of 1 over h minus 2 plus 1 over 2, all over h. And so now I want to get rid of the fractions. So I need to multiply by the least common denominator. So that's just 2 times h minus 2. So when we multiply in this first term, this one right here, the h minus 2's cancel. So it's just 2 times 1, which is 2. When I multiply it times the second term, the 2's cancel. So it's just h minus 2. And then on the bottom, we just get 2h times h minus 2. And I forgot the limit. So that's the limit as h approaches 0. So now we can combine like terms on top, and the 2's cancel. 2 and negative 2. So this is h over 2, h times h minus 2. And now we can cancel out the h's. So this is the limit as h approaches 0 of 1 over 2 times h minus 2. And now I can plug in 0. So this is 1 over 2 times 0 minus 2, which is 1 over 2 times negative 2, which is negative 1/4. Okay. So that's the idea. So this is one of the applications that we're going to use more and more and more, especially when we get to chapter 3, and we'll give a formal name in that. But that's the limit of the average rate of change. So that's how you find tangent lines. That's how you find instantaneous rates. The last thing in this section is what's called the sandwich theorem. So suppose that you have three functions, g of x, f of x, and h of x. And f of x is always between g of x and h of x for all x. So basically the idea is if you've got three functions, here's g of x, here's h of x, and then f of x is always between them. Okay, so that's what we're saying. Except possibly at a point C. Okay, suppose that the limit of g of x equals the limit of h of x. So if there's some point where their limits are the same, like right here, then the limit of f of x has to also be the same. So if you can show that a function is between two other functions always, at least within an interval, then the limit of that function has to be the same as the limit of the two outside functions anytime the limit of the two outside functions is the same. So if you have two functions, one on top of the other, and they come together, then the limit of all three functions will be the same at that point. So for example here, if I want to find the limit, if I know g of x falls between 2 minus x squared and 2 cosine x, and I want to find the limit of g of x, well, what I could start by doing is finding the limits of the two outside functions. So I could do the limit as x approaches 0 of 2 minus x squared, and I could do the limit as x approaches 0 of 2 cosine of x. Okay, so we do those by just plugging in the values. So 2 minus 0 squared is 2. 2 times cosine of 0. Well, cosine of 0 is 1. So 2 times 1 is 2. So the limit as x approaches 0 of g of x must be 2. Right? Because these two, it's between these two functions all the time. We know that they share the same limit, and therefore g of x must also share that limit. So that's the kind of thing we're looking at here. So suppose that the inequality is 1/2 minus x squared over 24 is less than 1 minus cosine of x over x squared, which is less than 1/2. Hold true for all values of x close to 0. What, if anything, does that tell you about the limit as x approaches 0 of 1 minus cosine of x squared? Well, what do we know? We know it's always between those. So that means if the limit of these two functions, this one and this one, are the same at 0, then that is also the limit in the middle one. So we can find the limit as x approaches 0 of 1/2 minus x squared over 24. So that'd be 1/2 minus 0 squared over 24, which is 1/2. And the limit as x approaches 0 of 1/2 is a constant, so that's going to be 1/2. So we know the limit as x approaches 0 of 1 minus cosine of x over x squared must be 1/2. Because as we get close to 0, this function is always between those two functions. Okay, so that's the idea. So if you wanted to, you could go and pause the video at this point and try the last problem on your own. And then when you hit play, we'll go through it together. Okay, so same idea as this one for the first two. We know f of x is between these two functions. So that means if the limits of these two functions are the same at 0, that'll be the limit of f of x. So this would be the limit as x approaches 0 of 5 minus 2x squared, and the limit as x approaches 0 of the square root of 5 minus x squared. So that's the square root of 5 minus 2 times 0 squared. Square root of 5 minus 0 squared. So that's the square root of 5 and the square root of 5. So the limit as x approaches 0 of f of x must equal the square root of 5. Okay, so that's it for how do we find limits. So these have been algebraic approaches to finding limits of functions. So don't forget to do the homework assignments for this week. And if you have any questions, feel free to call, text, or email me, and we can talk about these problems.